Okay, let's look at this third problem here. And we're going to do a combinatorial argument to prove this. However, we're not going to start on the left-hand side. We're actually going to start by looking at the right-hand side. So when we're looking at the right-hand side, we notice that we're adding a bunch of terms, right? And each term consists of the product of two quantities, right? So 1 times n, 2 times n minus 1, k times n minus k plus 1. And the next thing we note is that the sum of these terms is always n plus 1. So if I'm looking k plus n minus k plus 1, when I add that up, I'm always going to get that the sum is going to be equal to n plus 1. So I see this 3 here, and I'm thinking, imagine if I'm trying to add up the number of ways to choose 3, so like this will be the first item. This is the second choice. And then this is the third choice. Right? Remember, for the product rule, we can have it so that the middle choice, we're always having the second choice be one specific number. So for instance, say we are assuming that whatever is this object or this element is going to be in our set. Well, now we have 3 choices for what goes here, and what would that be? N minus 2 choices for what goes here. And this is assuming that one of our choices is going to be this 4th item right here. And I feel like I'm not doing a good job of explaining it, but this is reminding me of the donut problem that we did, where we had a number of donuts, and we were trying to divide the donuts into different flavors. And what we said was, basically dividing the donuts into the different flavors, you're going to put them into different bins, and you now are arranging the donuts and the barriers. So if I have a barrier here, and I'm asking how many locations can I put 2 more barriers, one to the left and one to the right, then the right-hand side represents the number of ways that we can add 3 barriers, counting by where you place the middle barrier. So if our task is to place 3 barriers, among these n plus 2 spots. And the way you count it is you can say, hey, I'm going to organize the number of ways to place the barriers by where I place the middle barrier. So place middle barrier, because if you have 3 barriers, then you've got a left barrier, a right barrier, and a middle barrier. So place a middle barrier in the second spot. Okay? Or you can place it in the third spot. Let me resize. So second spot. Or the third spot. Or the 4th spot. All the way down to the n plus 1st spot. right? So here's the thing, my barrier, I'm gonna draw my barrier. So we've got 3 barriers to place. And we're saying, where are we gonna place the middle one? Well, you could place it here in the second, or you could place it here in the third, or you could place it here in the fourth, or you could place it here in the fifth, so forth and so on. And then the last place would, for the middle, would be, you could place it in the n plus first spot. So in total, I have n plus 2 spots, and I am trying to place 3 barriers in the n plus 2 spots. What remains will be, well, if I have n plus 2 spots, and that's 3 barriers, then I have n minus 1, objects, n minus 1 donuts, if you will. So the remaining, so let's put here the remaining spots will be filled with the donuts. So the right-hand side is now counting the number of ways to place 3 barriers among these n plus 2 spots. Because if I'm going to place the 3 barriers here, I have to place the middle one somewhere. So I can organize a total number of ways to place the 3 barriers based on where I'm going to place the middle one. Now let's count. How many different ways are there to place the middle barrier in the second spot? Well, it's the middle barrier, so I have one option for where to put the first barrier, and I have n options for where to put the second barrier, or the last barrier. So I have 1 times n different ways to do this. 1 times n different ways. What about placing the middle barrier in the third spot? So we have our 3 barriers. How many different ways are there to place it in the third spot? Well, now I have 2 options for where to place the first barrier, and I have n minus 1 options for where to place the last barrier. So 2 times n minus 1 different ways to place the middle barrier. For the fourth one, you get the idea, right? We see a pattern here. It'll be 3 times n minus 2, because you have 3 options for placing the first one to the left, and you have n minus 2 options for placing the last one to the right, ... And then how many different ways can you place the middle barrier here? Well, now you have n times 1, okay? So here it'll be n times 1 different ways. So the left-hand side represents the number of ways to place 3 barriers among n plus 2 spots. You're going to count based on location of middle barrier. The right-hand side, the right-hand side, that's the right-hand side. The right-hand side is just saying, hey, where do we put 3? So I've got n plus 2 spots, and choose 3 of the n plus 2 spots to put your 3 barriers. Yeah. And we could even kind of go into detail about why is the left-hand side going to be n plus 2 choose 3. That's n plus 2 times n plus 1 times n divided by 3 times 2. Yeah, so this is my right-hand side, or my left-hand side, sorry. Okay, I've got my 3, and I'm asking how many different locations, how many options do I have for where to place the first one? That's going to be n plus 2. Once I place the first one, I now have n plus 1 different options for where to place the second one. Once I place the second one, I now have n options remaining for where to place the third. So that's the n. So this numerator represents it represents a permutation. I am counting the number of different ways to put or to place the 1, 2, 3, assuming that the order in which I place them matters, right? So I'm placing this one first, then I'm placing the middle one second, then I'm placing the last one third, right? Divide by 3 times 2 because there's actually no distinguishing among the 3 barriers. So say instead of calling these barriers just, 3 sticks, imagine if we called them A, B, and C. Now, I've got 36 or n plus 2 different ways to put A, and then B, and then C, right? The number of ways would be n plus 2 times n plus 1 times n, right? And now I've overcounted because I don't have distinct elements A, B, and C. They're all sticks. How many ways have I overcounted? Well, for each way, I've overcounted by 6 because there are 3 factorial different ways to express ACB. Because I could have ACB, I could have ABC, I could have BAC, BCA, and then, CAB, CBA, right? And all 6 of these, let me go ahead and write it down. It'd be the CAB, and then CBA. So all 6 of these represent the same placement when I'm using the barriers instead of using the letters, right? So that's why I need to divide by 6 because I am overcounting by a multiple of 6, right? Because each way is represented 6 different ways, okay? Okay, so that is, I guess that one wasn't all that short, but hopefully it was helpful to kind of see how sometimes you might work from the left, sometimes you might work from the right, and you can understand these identities in terms of counting, usually elements of sets or something like that. All right, as usual, let me know if you have any questions.